Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. I want to close this topic of equations with some examples, some simple examples, okay, which give the student some confidence that it's the same thing, the complicated set of equations result in the simple equations in case of simpler systems. Okay, so first one thing I want to do is that I'd like to derive the Euler-Bernoulli beam equation using force balance. Okay, so let's see, we have our beam, top surface, bottom surface, the middle line, neutral surface. So we'll do pure bending. Okay, that means the neutral axis does not stretch. Okay, this is my x, that way is my y, vertical is my z. Okay, so now what do we have? We have my axial displacement u is equal to z times beta, okay, and with epsilon xz going to 0. Okay, what is the epsilon xz? It is del u del z plus del w del x. Okay, so what does this result in? From here this gives me beta plus del w by del x. So if I set that to 0, I get a definition for beta. Beta is equal to minus del w by del x. Therefore my u is equal to minus z del w by del x. Okay, and therefore del u by del x, which is my epsilon xx, is equal to minus z del 2w by del x square. Okay, just to remind you, by arguments we have set all other stresses except sigma xx to 0 and all strains except xx to 0. Okay, that's our starting point. Okay, now what do we have? If del w del x is positive, okay, and z is positive, that means I am at somewhere over here, then my u is negative. Okay, so what is my sigma xx? Sigma xx is E epsilon xx, which is equal to minus Ez del 2w by del x square. Okay, now the moment resultant. What is that? Mxx is equal to integral minus h by 2 to h by 2 minus e z square del 2 w by del x square dz. Okay, the vertical displacement is w, okay, w of x, that's, and this way it is u. So this gives me minus e h cube by 12 del 2w by del x square. Okay. If del 2w by del x square is positive, that means you can say the beam is bending like this. Okay, then what happens? Then my moment is negative. Okay, so that sets the moment convention. So what is the moment convention? Moments that give this curvature, that means this picture, are negative, and therefore the positive moment convention is this. This is the positive moment convention. I have mxx and I have mxx plus del mxx del x dx. Okay, and accordingly I will put negative shear force on the negative side and positive shear force on the positive side, x plus dx. Okay, so now Euler-Bernoulli beam with all its assumptions ignores rotational inertia, and therefore the moment equilibrium. If we do a moment equilibrium, okay, what do we get? We get v of x dx by 2. So let us say this is positive, into the width b. Okay, so the width into the plane is b, then plus v of x plus dx into dx by 2 into b. Okay, then mx plus mxx into b minus mxx plus del mxx by del x dx into b, because these are resultants, that is equal to 0 for me. Okay, so if you sort this out, I will get Vx is equal to del mx x by del x. Okay, this is one equation you will get. Okay, then we need at the dynamical equation for vertical motion. For vertical motion, which means the integrated form of vertical shear stress is required, cannot be 0, which means that epsilon xz being 0 in the beginning is an unrealistic assumption. That is the whole point of the discrepancy. Okay, so the epsilon xz being 0 is unrealistic. Why? Because we need vertical shear integrated for dynamical movement in the vertical direction. Okay, so now what do we have? We have minus v of x into the b plus v of x plus dx into b. That now gives me density, length of the element, width of the element, height of the element into acceleration. Okay, so if I do a Taylor expansion, I get Vx plus del V by del x dx into AB. Okay, so the resultant is del V by del x is equal to rho h w double dot. Okay, and V is what? V is del mx by del x, so that means del 2 mxx by del x square is equal to rho h w double dot. But finally my mxx is this, and therefore I get E h cube by 12 del 2 w by del x square plus rho h w double dot is equal to 0. Okay, usually we put in b over here, we put in a b over here, and this becomes the area w double dot. So I get EI del 4 w by del x4 plus mass per unit length rho a w double dot equal to 0. Okay, so that's how you get the Euler-Bernoulli beam equation using regular force balance. Okay, now next what I want to do is I want to go through the steps presented in the book for Hamilton's law, okay, for the case of a rectangular plate. Rectangular plate, flat rectangular plate. Okay, so if we have a rectangular plate geometry, my A1 is going to be 1, A2 is going to be 1, R1 is going to be infinity, and R2 is going to be infinity. Okay, so in plane movement, that is U1 and U2 are uncoupled now, are uncoupled from U3 motion. So we can derive equations of motion just for U3 using Hamilton's law. Okay, so we will do that. So let us see the kinetic energy term. Kinetic energy term, okay, Tk. Now we include only the transverse, half rho U3 dot square dV. Okay, so that my K is equal to 1/2 rho integral alpha 1 integral alpha 2 integral alpha 3 u3 dot squared d alpha 1 d alpha 2 d alpha 3. Okay, so I am sticking to this notation because students will be now seeing the textbook, and everywhere it's alpha 1, alpha 2, alpha 3. But you keep in mind that for this rectangular plate, alpha 1 is x, alpha 2 is y, alpha 3 is z. Okay, if anywhere I replace one with the other, that should be okay. Okay, but I will stick with the alpha notation. Okay, so this alpha 3 integral is from minus h by 2 to h by 2, and this is, you know, the volume element. It can even be dx, dy, dz. Okay, so now u3, from our Love's assumption, u3, which is a function of alpha 1, alpha 2, alpha 3, what did we write? We said is alpha u3 alpha 1 alpha 2. There is no alpha 3 dependence. So this alpha 3 integral will give me an h outside. Okay, so I will get k as 1/2 rho h integral alpha 1 integral alpha 2, okay, u3 dot square d alpha 1 d alpha 2. Okay, so now if we put this in the way it appears in the Hamilton's law, delta k dt, that becomes equal to rho h integral t1 to t2 integral alpha 1 integral alpha 2 u3 dot delta u3 dot d alpha 1 d alpha 2 dt. Okay, we will do the time integral. These steps must be now familiar to you. Do the time integral. So what do we get? We get rho h t1 to t2 delta k dt is equal to rho times h integral alpha 1 integral alpha 2 u3 dot delta u3 dot t1 to t2 minus the second term, which is integral alpha 1 integral alpha 2 integral t u3 double dot delta u3 d alpha 1 d alpha 2 dt. Okay, now Hamilton's law says that the system, a dynamical system, moves between two state points, one at t1, one at t2, and these are known state points, and therefore their variations are 0. So I am sorry, this should have been delta u3, not dot, delta u3, this is the first term. Okay, delta u3, and therefore delta u3, the variation is 0 at t1 and t2 because it is specified, and so this temporal term goes to 0. Okay, and we are left with this here. Okay. Now, in keeping with all the signs etc., the form of the law with signs I am going to use is T1 to T2, the kinetic energy minus the strain energy plus the energy from the boundary forces plus the energy from external loads dt equal to 0. That is the form I will use. Okay. So, if we draw a picture to denote the boundary forces that come in, so this is my middle surface alpha 1 or x, that is my middle surface alpha 2 or y. Okay. Now, on these two surfaces, what are the forces that can come from the boundary? Okay. So, one is we can get an M22 moment, which is M22 star. Okay. Therefore, an M22 star here. So, we are considering only pure bending. Okay. So, we will take terms related to that only. Then we can have a vertical shear force resultant, which is Q23 star and a Q23 star here. Okay. At an okay, these are at alpha 2 constant surfaces. This is an alpha 2 constant edge, that is an alpha 2 constant edge. Okay. And lastly, we can have a shear related moment, which will be in the plane of this surface like this, M21 star and an M21 star here also, M21 star. Okay. So, how will the boundary term look like? The boundary term related looks like an integral over alpha 1, okay, M21 star beta 1 plus M22 star beta 2 plus Q23 star U3 d alpha 1. Okay. So, M21 is related to this rotation in the plane of that surface, that is beta 1. Okay. Whereas M22 is also related to a rotation, but this is out of plane. This is out of plane. Difficult to draw, but it is out of plane. Whereas this is in the plane of this surface. Okay. So, that is this. So, now with this logic, if we write the full boundary term, okay, so the variation of the integral of the boundary term dt is equal to integral T1 to T2 integral alpha 1 M21 star, the variation lands on beta 1 plus m to 2 star delta beta 2 plus q to 3 star delta u3 d alpha 1. Okay, so I have taken this variation inside. This is at an alpha 2 constant edge, plus the integral from t1 to t2 integral alpha 2, the other set of external possibilities delta beta 2 plus m11 star delta beta 1 plus q13 star delta u3, okay, d alpha 2, this is at an alpha 1 constant edge. Okay, and lastly for our plate, okay, for our plate we are only looking at transverse motion, and so there will only be a transverse force Q3, no forces in any of the other directions. So the variational term related to external load dt is equal to delta integral t1 to t2 integral alpha 1 integral alpha 2, the force into displacement d alpha 1 d alpha 2 dt. Okay, now taking the variation inside, integral t1 to t2 integral alpha 1 integral alpha 2 q3 delta u3 d alpha 1 d alpha 2 dt. Okay, so there is a force per unit area, that should be the units, force per unit area. So you multiply that by this area element, you get a force. So that's a force per unit area. You multiply by the elemental elements and you get a force, and that into u3 is the energy given there. Okay, so now q3 is specified, and therefore the variation ends up on u3, you get delta u3. Okay, so we have the kinetic energy term, the boundary term, and the loading term. So what is left is the strain energy term. Strain energy. Okay, the strain energy is a big derivation. So what I'll do is I'll stop the lecture here and continue in the next class. Thank you.